In this chapter, we will be using calculus as a tool in curve sketching. In this video, we'll be sketching the curve of x over the square root of x squared plus 2.
Okay, next we're going to take a look at the function f of x is equal to x over the square root of x squared plus 2. This has also got a kind of an interesting little feature to it that's worth spending some time looking at. First of all, let's take a look at the domain. Now when I see a radical there, and a denominator there for that matter, I'm concerned. But when I take a look at this here, first of all, when I consider the denominator, is there anywhere where this thing could go to 0? And the answer is no. Anytime I take a number and square it, whether it's positive or negative, I'm going to get a positive result. And when I add 2 to that, that's always going to be positive. So there's no way that this is going to become 0 here. And that's actually good news, because when I take the square root, what I'm trying to look for here when I'm looking for the domain is I'm looking for any time or any points along the x-axis where that creates the radical or the root of a negative. And I just said these are always positive, so that never happens. So actually my domain here is going to be x is an element of the reals. Beautiful. 2. Let's take a look at the intercepts. And again, I'm going to grab the y-intercept first. F at 0 is going to be 0 over the square root of 0 squared plus 2. And this is going to go to 0 as long as the denominator doesn't go to 0, and it doesn't. Because 0 squared is 0 plus 2 is 2, and then the square root of 2 here. So that's just going to be 0, which is good. The x-intercept, I am looking at, I am looking at where f of x equals 0, and that's going to be x over the square root of x squared plus 2. And remember, and I'd said this before, if I've got this rational expression here equal to 0, it's not the denominator doing that. Okay, the denominator can't create a 0 here, so it's got to be the numerator going to 0. So it's got to be where x is equal to 0. So notice in both cases here, my x and y-intercept both suggest that the origin is an issue. Okay, the origin is where this thing is crossing the axes. Good. 3, symmetry. Okay, so if I take a negative and plug it in, I am going to get negative x in the numerator. And then I'm going to get negative x squared plus 2. Now, bear in mind how that looks down here. I'm replacing the x with a negative x. Now, because in the original function, x was being squared, when I replace it with negative x, it's negative x being squared. And that's actually just going to become a positive. So look what happens here. The negative basically disappears. This is essentially exactly the same as the negative of the original function, which makes this thing odd. Okay, so it's got, therefore it's got rotation symmetry about the origin. Whoops. That's right, I wanted to say rotation symmetry. Good. Good, so actually, I can kind of guess at this without too much work. I can kind of do half of the work here, if you will, and still get the graph here. But that's okay, I'm going to go through and do the whole thing anyway. But that's just going to, basically, when I'm done here, if I look at my graph and notice that it's got rotation symmetry on the origin, I know that everything's nicely consistent here. 4, asymptotes. This is a rational, so I am going to be expecting an asymptote here. Now, it's going to have no vertical asymptotes, okay, because the denominator doesn't go to 0 here. But have a quick look at this. Notice that the degree, and actually I'll write the function out again here. Notice that the degree of the numerator and the denominator really are the same. Okay, it's a linear in the numerator, it's a linear in the denominator because it's the square root of an x squared. Now, I'm going to take the limit then as x goes to infinity of x over the square root of x squared plus 2. I want to see how this thing behaves as I go really, really far to the right. Now, when I do that, when I get really, really big values of x, when you square a billion, adding 2 really doesn't change the value significantly. So when I get really, really big values of x, this plus 2 is essentially irrelevant. And so then I've got the square root of x squared, which, when you think about it, everybody, is kind of like the absolute value of x. Now, when I go to positive infinity, it doesn't really matter because I'm going to get positive numbers squared, which is a big positive number. The square root will be a positive number, and then it's basically x in the numerator. So this is going to simplify down to x over x, or just 1. Which is kind of neat. But the behavior is a little... Whoops, sorry. Dang it. I'm anticipating the answer. When I go to negative infinity, something a little different happens here. When you go to negative infinity, bear in mind, just look at the denominator here. When you get really, really big negative numbers here, like negative a billion squared, again, adding the 2 does nothing to it. So I'm really just looking at this. When you take a negative number, a really big one, and square it, you get a positive. The square root of a positive number is a positive number. But bear in mind, I'm taking the limit as x goes to infinity, negative infinity. So the numerator is going to be negative. The denominator will be positive, but they're going to be the same value. Because really what this is like taking the limit as x goes to negative infinity of x over the absolute value of x. So even though they got the same number, the numerator is going to be negative, the denominator is going to be positive. This is basically going to be negative 1. This is what makes this graph unique, is I've got 2 horizontal asymptotes. I've got a horizontal asymptote at y is equal to 1 and y equals negative 1, depending on which direction you're going. That's why this was an interesting question to look at. Now let's take a look at intervals of increasing and decreasing. Now at this point here, actually, to be honest with you, we could probably draw a half-decent sketch even right now without having to go through the rest of this. But it is what it is, so let's go through, let's do the calculus here. So f primed of x, let's figure what that is. So again, I'm going to use the quotient rule. So the derivative of the numerator is 1, and then multiplied by the denominator, x squared plus 2 to the half, minus the numerator multiplied by the derivative of the denominator to the negative 1/2 multiplied by 2x all over the denominator squared. Okay, well, I got a bunch going on here. Now, first of all, notice the 1/2 and the 2 are going to cancel. The smallest exponent on the x squared plus 2 is actually negative 1/2, so I'm going to take that out. Negative 1/2. That is going to leave me with 1 minus, and notice I've got 2 x's there, so 1 minus x squared all over x squared plus 2. That's going to drop down to the denominator, so I'm going to get 1 minus x squared all over x squared plus 2 to the 3/2 when I bring that down, because this is all to the 1, and I'm just going to add that 1/2 down there. So I want to double check that I did that right there. Oh, shoot. No, I didn't. No, I did not. Okay. I'm sorry. I didn't take out... I got to go back up a step here. I did not take out x squared plus 2 to the 1/2. I took x squared plus 2 to the negative 1/2. So when I factor that out of x squared plus 2 to the 1/2, I got to divide those powers, which means subtracting exponents. And 1/2 minus negative 1/2 is 1. That actually is going to leave me with an x squared plus 2 there to the 1 minus x squared. Oh, this is a lot nicer than I was about to make it. Whoa, wow, I'm glad I caught that. Now, again, for those that aren't seeing how that works here, it might be more obvious if you just multiply this through. If you just multiply this back through, you'll see x squared plus 2 to the negative 1/2. If you multiply that by x squared plus 2, it'll get you x squared plus 2 to the positive 1/2. So anyway, right now that factor up front there is going to move down. The x squared is going to cancel. I'm going to be left with a 2 here. That's beautiful. Absolutely beautiful. Now, where is this function go to 0? It doesn't. Okay, because the numerator is just a constant and it's 2, and so there's nothing here that's going to cause it to go to 0. Where is it undefined? It's not. So whatever value this is taking on, it's always going, and I mean value, I mean sign, whether it's positive or negative, it's always going to be either positive or negative here. And it turns out this thing is always positive. Okay, so we know that f primed of x is greater than 0 on the interval here where x is an element of the reals. That means this thing is positive or increasing on the interval negative infinity to infinity. It's, in fact, it's strictly increasing. It is always increasing. That was wonderful. And so as a result, I can also jump to point 6 here and say there's no max or min here. Okay? There's no point that even suggests a maximum or a minimum. And I really like that first derivative here. Now, let's go through and let's investigate the second derivative. Let's take a look at concavity here. So let's just remember that function, 2 over x squared plus 2 to the 3 halves. Okay, so this is 7 now. My first derivative was 2 over x squared plus 2 to the 3 halves. And actually, I might write this as 2 multiplied by x squared plus 2 to the negative 3 halves, just because this is going to make the derivative a little easier. My second derivative will now be multiply through, that's going to be negative 3 x squared plus 2, what is that, to the negative 5 halves, multiplied by 2x. Alright, so what does that look like? Negative 6x over x squared plus 2 to the 5, whoops, that's not 100% clear, but to the 5 halves. Okay, now what does this tell us? Well, I'm interested once again in where the second derivative is positive or negative, is positive or negative for concave up and down, but I'm interested to find that where it goes to 0, or it's undefined. But just like the first derivative, look at that, that's not going to become undefined anywhere, so it's really just where it goes to 0, and it's going to go to 0 at 0. So this actually makes things a little bit easier. So if I plug in a negative value squared, just look at the denominator, negative value squared plus 2, 5 halves, the denominator will always be positive no matter what I plug in. So it's really just the numerator that's the issue, and if you plug a negative into that, the numerator becomes positive. If you plug a positive into the whole thing, the numerator becomes negative. So this tells me the second derivative is positive on the interval negative infinity up to 0, which means this thing is going to be concave up from negative infinity up to 0 and inclusive. The second derivative is going to be less than 0 on the interval 0 out to infinity, which means it's going to be concave down on the interval from 0 to infinity, including the 0. And so clearly, number 8, if I'm looking for a point of inflection or a cusp, and in this case it's definitely going to be a point of inflection, it's that origin again, 0, where x is equal to 0. Okay? And I can see that because the concavity is changing at 0. Okay, got everything we need. Let's graph this thing. Whoops. So I knew that my origin was the intercept, the x and the y intercept here. I also know it's my point of inflection. Okay, I have got an asymptote here at 1 and an asymptote at negative 1. I know, however, that it's going to be approaching the positive one only as you go to the right and approaching the negative one as I go to the left. If I think about my intervals of increasing and decreasing, it's always increasing. And then if I think about my intervals of concavity, it's going to be concave up here. See, happy face. Concave down here. All right. So now let's just take a quick look at this. So in this interval here, to the left, it's increasing, concave up, and it approaches this asymptote as I go to the left. Well, it's got to look something like that. Then it becomes concave down, still increasing, and it approaches this asymptote. So it's got to look something like this. Now, notice it doesn't go vertical here because the first derivative wasn't undefined there. So it just kind of levels out. Well, it doesn't level out flat, but it's just got a, a reasonable slope to it, and away we go. That's what that looks like. Interesting graph because of the two horizontal asymptotes.